Vectors are to do with, and they often don't actually come up for a little bit more advanced part of mathematics, but they're not too complicated to just work with on their own. So this is going to be our little reintroduction into vectors. Let me say reintroduction since this is a review video. If you weren't in class, I guess this is an introduction, but either way. Vectors are lines with some notion of direction. So I can draw this vector here. Well, I can also move the vector, and we still consider it to be the same vector once we move it. I care about the length of the vector and the direction that it is facing, but I don't care about where the vector sits. So this is why in class I keep using the analogy of like a car. A car is the same car no matter where you move it. A vector is the same vector no matter where we move it. We just don't turn the vector, we don't shrink the vector. So this vector is the same as this vector, and I can even draw it all the way down here, and this is the same vector. And I genuinely mean treating this graph paper as if it's like this XY plane. So we can draw our vectors in the XY plane. And the way that I have drawn these here, it's over 3, up 3, over 3, up 3, over 3, up 3. These are all the same vector. It is just moved across the XY plane. Now, to talk about the vector, to know exactly where we are or what this vector is, then we kind of have to know where we start and where we stop, right? Because again, I care about the direction that the vector is going. So if I told you that we occupy 2 points, and I told you we start here and then go this direction, then that's different than as if I drew the same vector in that same spot, but drew the same line in that spot, but said we go from the top point down like that. These would be different vectors because the direction is different. So even though I may have a line going from one point to the other, it's important to know which point do we start at and which point do we end at. And we call the point that we start at the initial point. And then we call the point that we end at the terminal point. And that is for every vector. Now, the initial point and the terminal point can be different depending on where we move the vector, but that just gives us a way of describing exactly where a vector can sit in a spot. So for the one that I've drawn here, this would be the initial point. And then we have to move the same amount over 3, up 3 to this terminal point. And again, this is the same vector. It's just about where it sits that we start talking about the initial and terminal points. So we can move these vectors around however we want. And let me even grab the tool here that lets me move what I draw around. Oh. This is the same vector no matter where I move it. So as I'm moving it around all over the place, this is the exact same vector. I am just moving it. We can move our vectors around and it's perfectly fine. Well, where would be a really nice spot to put the vector down at? Where is the nicest place to start on our XY plane? Well, there's a spot on the XY plane called the origin, 0, 0. So maybe that's the best start, or yeah, the best starting point for our vector. And it turns out that does make things really nice. So over here, when I had the vector all the way up here, it was a little hard to immediately tell exactly how far to the right and up that we moved, right? Like we had to look and count 1, 2, 3, 1, 2, 3 to say that we moved 3 to the right and 3 upwards. But if I start at the origin and I told you I terminated at 3, 3, what does it mean to terminate at 3, 3? Well, that means we went over 3, up 3. We don't have to count or do that work if we start at the origin. We just literally get to read what is that terminal point, 3, 3. Well, then we know exactly our vector goes up 3 over 3. So to that end, we really like to draw our vectors starting at the origin with the initial point and the origin. So we write a vector as in standard position, if the initial point is the origin, which again is just our fancy name for that coordinate 0, 0. And why do we like that so much? Well, again, then the terminal point gives us exactly how we need to move, 3 to the right and 3 up. Well, a really nice way of naming and describing our vectors comes from kind of writing it like this. So again, if I write my vector starting at the origin, then whatever its terminal point is tells you exactly how it moves, 3 to the right and 3 up. But it turns out this vertical movement and horizontal movement are exactly the two pieces that we need to uniquely identify our vector. So if I say you move to the right 3 and up 3, there's only one vector I can be talking about, and that's this one. If I say we go down 2 and then to the right 2, well, there's only one vector that goes from the origin to that spot exactly. And I said this was down 2 and to the right 2. Yeah. Well, to that end, one way that we like to write our vectors is actually in component form. And so we kind of describe it the same way as looks a lot like this. So I say for this vector, and I'm drawing an arrow like to let us know what vector I'm talking about. That's not its own vector. I want to say I go to the right 3 and then I go up 3. But instead of drawing it like a coordinate, I want to make it clear I'm talking about a vector. So I'm going to do these angled brackets right here. So this is what we call the component form of a vector. When we draw it by just saying, how far do you move horizontally? How far do you move vertically? So the coordinate form or component form, I'll use the same words, of this vector would then be, well, 2, -2. And to that end, I think it's very clear why we like to draw our vectors in standard position, because then it ends in the exact same coordinates that go into that component form of the vector. So to that end, I think this is a very natural way of describing our vector, and very great. Now, a side note, we like to represent our vectors with variables. So just like in math, we'll write a squared plus b squared equals c squared if we were in a right triangle. We like to represent things using variables. So if I represent a vector with a variable, I want to make it very clear that this isn't some number that I'm talking about. This is a vector. So I'll write the vector v, but I'll draw this little line over it to make it very clear that I'm talking about a vector. And then I can say this vector v is equal to 3, 3. And that's letting you know exactly what vector I'm talking about here. Then I could say vector W is equal to 2 comma -2. And now when I talk about vector V, you know I'm talking about this thing. And when I talk about vector W, you know I'm talking about that thing. But I make it very, very clear that I'm talking about a vector by putting this line or this ray, really writing a small vector over the variable, just to make it clear what kind of object we're talking about. Well, these vectors, we said that they all have length and direction. That's kind of what makes a vector unique. So this vector that I draw here is very unique from the vector that I draw just twice as long. These are different vectors, right? Because this component form for the red one that I drew, well, let me make this less messy. So this vector is 2 comma -2. And if I have a vector twice as long, then this one actually turns out to be 4 comma -4. So it's very clear these are going a different distance. These are separate lines, but they do happen to be going in the same direction. But I do care about how exactly far the vector is going, how long the vector is. So to that end, we have a notion of length for our vectors. Now, as far as in your own head, it's perfectly fine to call this length because graphically speaking, that is literally what this is. But vectors are sometimes used to represent like physical things, well, physical objects, non things that are not physical objects. So sometimes they use vectors to talk about gravity. So to that end, you can talk about like how far an object moves, but to talk about the force of an object, it's really weird to describe that as having a length, but it does have a magnitude. So we say the magnitude of a vector is the length, I can't spell, length in the x, y plane and we write it's kind of like how far the vector is from 0. Well, if I'm talking about a real number, so something like 5, then I say how far is 5 from 0? Well, that answer is just 5. If I talk about -5 and I say how far is that from 0, then that is 5 away from 0. So in that sense, for real numbers, to do the distance from 0, we just take the absolute value. So for our vectors, this length is its distance from 0. So we draw the magnitude with something that looks like the absolute value, but we actually put 2 lines here just to make it really clear that we're talking about the magnitude of a vector, not the absolute value of a number. But you should think of it kind of like the absolute value for a vector. It is still the distance from 0. Well, how do we find the distance from 0? Well, this looks a lot familiar, I think. If the blue line is the length of the vector, then I can make this line here, and this would be 3. And then I make this line for the horizontal distance, and that would also be 3. And now the question is, if I know that bottom side of this right triangle is 3, and the other side is 3, then how long is the hypotenuse? We remember a theorem that c squared is a squared plus b squared. So c is just that square root. And it turns out that is exactly our formula for magnitude. It is just the square root of x squared plus y squared, where x and y are those components of the vector, where v is equal to x comma y. So that is how we find the magnitude of a vector, which in our head is really just the length of the vector. Great. Well, now the last detail about the vector that kind of helps us uniquely determine what our vector is the direction that it's facing. Well, what kind of object do we have in trig that helps us talk about directions? And that is angles. So in order to describe what direction a vector is facing, a really common thing to do is to talk about the direction angle. Well, let me try and clean this up just a little bit here. If we have our vector here, 3, 3, and I want to find the angle that this vector is facing. Well, I'm going to draw it in standard position. So if maybe we were looking at this vector, then let's move it here to be in standard position. And then we're going to talk about the angle here, right? We're really used to talking about angles in terms of their standard position, that is from the x-axis upwards, or sorry, counterclockwise is probably a better way to describe that. And that's exactly how we're going to talk about the direction angle for our vector. So we're going to draw our vector in standard position, that is starting from the origin, and then we're going to try and figure out what angle that this is at. So really, we are looking for this theta that we move there. Well, first things first, I would say, what I'm trying to make my wording make sense here. Now, if this was something on the unit circle, if this was a coordinate on the unit circle, so let's maybe draw our unit circle here. If this was here, and I told you that this point was root 2 comma root 2, do we know what angle corresponds to this x and y value? Yeah, we would say, well, that's just pi over 4. And then we'd immediately know that theta would be pi over 4. Well, in this case, we're not really on the unit circle, so we can't really approach it directly like that. So let's try and think of another way to talk about that angle. Well, let me redraw the vector entirely. So up 3 over 3, landing right there. So I know that this vector ends at the point 3, 3. Well, let's kind of do the same setup that we did when we made the right triangle to find the distance, to find the magnitude. When I draw this right triangle, I know this side is 3, and this side is 3. And this angle is exactly the angle that we're looking for. Well, is there any kind of trig function that we know that relates the opposite and adjacent sides of a right triangle? And we play the Jeopardy theme song music while we just kind of wait for a second. A trig function that relates the opposite and adjacent side of the right triangle. That is tangent. Tangent of theta should be equal to opposite, which is 3, over adjacent, which in this case turns out to also be 3. So if tangent of theta is 3/3, well, that turns out to be 1. Well, then the question is, for what value of theta is tangent equal to 1? And it turns out this is a nice angle, and I actually spoiled it earlier because it turns out that theta here is actually pi/4. So in this case, we would say our direction angle would be pi/4. The angle inside of our triangle right there. Well, not all vectors turn out so nicely. In fact, let's start over with a different vector that makes this problem look a little bit worse. All right. So if we draw our XY plane, and I'll say this is 1, 2, 3, 4, 1, 2, 3, 1, 2, 3. Then let's talk about the vector negative, sorry, 3, -2. I can do better than that. Hold on. Let's talk about this vector. Now again, this angle bracket means that I'm naming the vector. I'm not talking about this coordinate, but by design, this is the coordinate right here, is the same 3, -2. It's just that with these brackets, I'm naming this vector. So let's say V is this vector. Well, now we can do the same thing and say that we want to find tangent inverse of, now when we make this triangle, again, we do opposite over adjacent. Well, opposite side is going to be the vertical. So this is -2, and adjacent is 3. So we have an X and a Y. So we do tangent inverse of opposite, which would be the Y, over X. But in this case, we get tangent inverse of -2 over 3. Well, hold on. In that last example, it gave us this really nice angle right here because we were in quadrant 1. But tangent inverse doesn't give angles that are always positive, does it? Tangent inverse has those weird conditions with its restricted domain. Tangent inverse gives angles from -pi/2 to pi/2, like this. So it's only the right side of the unit circle, but even worse, it's not even from 0 to 2 pi, it's from -pi/2 to pi/2. So we're in this quadrant, sorry, quadrant 4, then the angle inverse tangent is going to give us will be negative. And in fact, let's do this in our calculators. We can do tangent inverse of -2 over 3. Sorry, I'm slow at typing this. And our calculator gives us about -33.69 in degrees. Well, again, we don't really want to talk about angles that are negative, it's really nice for us to have our angles from 0 to 2 pi. So how do I find something coterminal, so it sits in the same spot as that angle, but is positive? Well, I can add 360 degrees. And that gives me a coterminal angle, but this time it's going to be positive. So add 360 to that, and this turns out to be 326.31 if we're rounding to 2, to the second decimal place. Perfect. So this is the direction angle for there. But what happened there wasn't really special to the facts, or like the numbers that we had in particular. What ended up mattering is kind of about where the angle sat, or where our vector sat, what quadrant we were in. So here, now let's talk about the direction angle. The direction angle is the angle the vector makes in centered position. And we figured out that we get theta was tangent inverse of y over x. That's what we said right here. Now, if we were in quadrant 1, we didn't do anything to that. But if we were in quadrant 4, we had to add 360 to that angle. So let's do plus 360 if we're in quadrant 4. But again, tangent inverse only gives us angles from minus pi over 2 to pi over 2. What would we needed to have done if we were on the left side of the unit circle? So let's say I had a vector over here, and I wanted to find its direction angle. Well, tangent inverse would give me some direction angle here, but I would need to find how it sits there. Well, we noticed that the vector here and the vector that tangent inverse thinks we look like kind of are flat with each other. So how far apart are these two angles if they make a flat line? Well, that's 180 degrees. Likewise, if I were in quadrant 3, then that would be negative y and negative x, which tangent would think looks the same as positive y and positive x, which tangent inverse would think would be this vector. So what is the angle difference between these two vectors? Well, they make a flat line, so this angle is 180. So whether we're in quadrant 2 or we're in quadrant 3, then we have to add 180. But again, very nicely, if it turns out that we're in quadrant 1, we don't have to do anything. Tangent inverse does a great job of figuring that angle out all on its own without doing any of that special work. Great. So this is chapter 14, pretty much in its entirety, an introduction to vectors, what they look like, and these very basic properties. Now again, a vector is just direction and magnitude. So if you know the direction we face and we know how long the vector is, well then when we draw it in center position, it's going to sit in the same spot as any other vector with that direction and magnitude. So if I told you aim pi over 4, and then your vector is 5 units long, there's only one vector that could be. So again, our vectors are uniquely determined by just how long they are and what direction they face. And there's two different descriptions that we can really get from that. So we can do this component form that is just x comma y, or we can talk about the direction angle, this theta, and the magnitude. Well, if I have an angle, if I have a direction angle, can I get the main vector back from that? Well, what two functions do I have where I plug in some angle and it gives me the coordinate on the unit circle? Well, that would be cosine and sine, where cosine is this x value and sine is this y value. Well, then we have to know how long our line is. And once we do that, if I have a point here and I want some point that is twice as far out, how do I find that point? So let's say that this black dot was 1 or -1, comma 1. How do I find the point that is twice as far out? Well, that is genuinely just go twice as far to the right, go twice as far to the up. So -2, comma 2. We just multiply each coordinate by 2. So if I tell you how long the line is, then we just multiply these coordinates here by that length. But we can call the length something in particular. We name that the magnitude. So I'm going to draw this in a really fancy way. The magnitude of v times cosine theta and the magnitude of v times sine theta. So instead of telling you exactly just how far did we move to the left or right and up and down, I also could have just told you what is our magnitude and what is our direction angle. So this kind of gives us two different ways of constructing our vectors. But what we'll really work with are the x and y's. We're not really going to do this form as much, but it's still important to know and to be able to do. Yeah. Very good. All right, so that is, I think, now fully, completely, and finally all of our chapter 14. Yes, chapter 14 content. Very good. That's vectors. A really basic introduction.